All right, so we're on 1B.3 applications of rates of change. Basically, we're applying our knowledge of function notation and average rate of change to these situations. So you just took your quiz over average rate of change. So hopefully you still remember that the average, let's try that again. It didn't want me to write. That when you're finding the average rate of change, yeah, that's beautiful. A rock, it's going to equal f of b minus f of a over b minus a. And that's because you're given an interval from a to b, correct? So it tells you what an interval means. You have a starting and a stopping, and then you're evaluating at those points only. Make sense? Because you're averaging what's taking place in between. When you get to calculus, you can be a little more specific and find the exact rate of change at those given points, but we're not in calculus. This is pre-AP Algebra 2, so it's not a problem. All right, so what we're going to go through is applications that utilize rates of change. And they're pretty basic as far as like, oh, that makes sense. So our first application would be a physics application. The speed of a car. So a car travels from one city to another. It covers a distance of 150 kilometers in 3 hours. Okay. So when you're thinking about, okay, you're starting and stopping. So your interval from here is I'm starting at 0 and I'm ending at 3. Does that make sense? So my interval of time is 0 to 3. So I would need to know what is the f of 0. Well, the f of 0 is if I'm not driving anywhere, how far have I gone? 0 kilometers. And then your f of 3 is going to be after 3 hours, how far have I gone? 150, right? So I've gone 150 after 3 hours. When I'm calculating this, remember, average rate of change is your A and your B. So f of A minus f of B minus f of A over B minus A. So the A rock here would equal f of 3 minus f of 0 over 3 minus 0. Well, f of 3 is what? 150. F of 0 is 0. 3 minus 0 is 3. So in this case, I've gone 150 over 3, which equals, what is my speed? $50. Thank you. 50. And then remember, we talked about your unit rate. Your unit rate is what does your numerator describe per your denominator? My numerator is describing the what? The distance. So it's kilometers per, and then my denominator is describing my hours. So kilometers per hour, and that would be my average rate of change as I'm driving from one city to the other. Okay. Is it a guarantee that I'm driving 50 kilometers per hour? No, that's why it's the average rate of change. Over the time, I may drive really fast, slow down, drive really fast, slow down. But this is my average rate of speed as I travel along. Okay. How do we feel about the physics application? So every time you're driving your car, you're A-rocking it. Just FYI at this point. Questions, comments? All right, next application would be a biology application when we're talking about population growth. Okay, so I would like for you to set it up. So we're going to read it, and then I would like for you to take a moment and set up what's your interval, and then identify your f of your A, f of your B, and see how far you can go. Okay, so the population of a town increased from 20,000 in the year 2000 to 25,000 in the year 2020. What is the average rate of a change of population per year over the period? Okay, so identify what's your interval, find your f of A and your f of B, and then find your A rock. You can talk to each other. Okay, so for this problem, what did you get for the interval? So your interval is based off of your independent variable. Is our population our independent or is our time, our year? The year. So your interval would be the 2000 to 2020 because that's describing your independent variable, right? That's what your interval is representing, is your independent, your X values. Okay. So then I need to find F of 2000. So in 2000, population was 20,000, right? And then F of 2020, it was 25,000. So then my A rock equals F of 2020, which is 25,000, minus F of 2000, which is 20,000 all over 2020 minus 2,000. How do we do? Yeah. All right. 25,000 minus 20,000 leaves us with 5,000. Okay. And then 2020 minus 22,000 leaves us with 20. Chop off these zeros. Remember the little rules. And now I'm just left with 500 divided by 2. 250. 250 what? There we go. 250 people per year. That's because our numerator describes the people. Our denominator describes the year. So that would be our unit label. Population growth. Did A-Rock run any different than before? No, it didn't. Okay. Meteorology application. Temperature change. The temperature in a city changed from 10 degrees Celsius at 8 a.m. to 25 degrees Celsius at 2 p.m. What was the average rate of temperature change? Okay. Well, this is where it gets a little tricky, right? So we have 8 a.m. and 2 p.m. How many of y'all know what military time is? Yeah, military. Military time allows for us to actually mathematically calculate this time over change. Does that make sense? That's because 2 p.m. is kind of confusing because is that positive? Is it negative? Like, how do I write that? But if we convert it into military time, can we then calculate our change in time over there? All right, so we're going to convert this military time. What is 2 p.m. as military time? 1400. There we go. And 8 a.m. becomes just 800. Y'all, 0800. My dad's ex-military. So yeah. Okay. So one of my interval here is going to be from 0800 to 1400. Because if you're catching on, a lot of times time is going to be our independent variable, right? So that's the interval we're analyzing over. And we know that at 0800, what was it? 10 degrees. And then at 1400, what was our temperature? 25. I now have all the pieces to my A-rock, correct? So now I'm going to calculate what is A-rock. Okay, so we have 25 minus 10 over 1400 minus 800. 25 minus 10 gives us 15. 1400 minus 800 gives us 600. So 600 is equivalent to what? 6 hours, right? 600 is equivalent to 6 hours. So we're down to 15 over 6. All right, so approximately what is that? What's 15 divided by 6? We get what? 2.5. Now, what is this 2.5 describing? What's our numerator describing? The degrees, right? The degrees in Celsius per, and then our denominator is describing our hour. So 2.5 degrees Celsius per hour is what it's increasing by over that time window. Okay, So as we do some math problems, we have to also use a little bit of math sense and just like okay, how can I calculate this based on what's being given to me? Again, has the math been that bad? It's just remembering how to set it up and what we're setting up, okay? All right, here you go. You're going to do a revenue growth economics application. A company's revenue grew from 1 million in 2018 to 1.5 million in 2023. What is the average rate of revenue growth per year? Go. I don't know why. My independent here would be the year. So when we set it up, that's our 2018 to 2023. So my F of 2018 would be my 1 million. I'm going to be lazy and just write 1M. My F of 2023 would equal my 1.5 million. Okay, so the AROC equals 1.5 minus 1 over 2023 minus 2018. So we have 0.5 over 5. Minus 0.5 divided by 5. Or what's 500,000 divided by 5? What'd you get? 100,000. So you end up, this really hurts, guys. My neck is killing me. All right, so I end up with 0.5, and I'm being lazy because I'm not writing the whole word out, but this is going to equal, that is not a 5. You see nothing. It's not meant to be a 5, Shauna. It's meant to be a 1. You were fine. The struggle is real. There we go. This equals 100,000. And what's our units? Dollars per year. All right. You're looking at a water level in a tank, engineering application. So you have a water tank is being filled and the water level rises from 2 meters at 9 a.m. to 8 meters at 12 p.m. What is the average rate of change? At this one, I want you to challenge. Just solve it. You don't have to identify if you are filling it and you recognize the pattern and you know what your independent and dependent. Because remember, all basically AROC is the change in your dependent over the change in your independent, delta y over delta x. So re-evaluate. Don't judge how it printed. Weird. Okay, so at this point, remember I said, let's see if we can just do it without having to write all of our lives out, right? All the information. So it's our change in our y over our change in our x, right? So in this case, our y's are what? Represents the what? The meters. So we're looking from 2 to 8, right? So our change in our y is 8 minus 2. Our change in our x is going to be how much time has passed. How much time had passed? And then, so 3 hours. 3 hours had passed. 8 minus 2 is 6. 6 divided by 3 is 2. So therefore, this would be 2 meters per hour of change. Yeah? Okay. All right. Again, fuel consumption, automotive application. A vehicle used 30 liters of fuel to travel 240 kilometers. What is the average rate of change, rate of fuel composition? Independent over your dependent. But you're dependent over your independent. What is the change? I gave you a hint. Think about liters per kilometer. All right. So we have 30 liters per kilometer as our end game, right? So that automatically gives us a hint as to what's our dependent and what's our independent, correct? And when we're setting up our units, it describes our numerator behavior over our denominator. So in our numerator, we need to talk about liters. So this is going to be our dependent variable. And our denominator, we need to talk about kilometers. So this is going to be our independent variable, right? So A rock is our delta y over delta x. So liters, so our change in our liters, well, we went from 0 to 30. And then our kilometers, our travel, we went 200 and from 0 to 240. Is there any real reason for me to include 0 at this point? Nope. I'm going to eliminate these zeros and reduce. That gives me 1/8, which equals what? What do we get? You get 0.125 liters per kilometer. So you have to follow what it's telling you to measure. So this is liters per kilometers. If it was kilometers per liter, then it would be 8. Because it's liters per kilometer, it's a 0.125. Because it's asking for your fuel consumption. So how are you losing fuel over time? Okay. All right. So to check that we completely understand how it works, we're going to kind of look at it from a table perspective, but also tying it together. So on your own, and then when you're done with the 2 questions, I would like for you to check with your peers. But it says a table of values for function g of x is given below. The table represents the height in meters of a ball thrown into the air after a certain number of seconds. So going back to a physics application, right? And so you have the times 0, 1, 2, 3, 4, and how high the ball is in the air at those specific times. I would like for you to calculate the average rate of change over the given intervals. So you have from 0 to 2 and 2 to 4. All right. And go. Actually, some degree probably was easier, right? Using the table. So it says on the table you have from 0 to 2, it wants you to analyze. So from 0 to 2 means that I need to find g of 0 and g of 2, right? So g of 0, you should have gotten 1. G of 2, you should have gotten 4. So calculating the A rock, remember that's the change in your y's over the change in your x's, which would have given you 3 over 2, which equals 1.5. What does your numerator represent? What's our numerator? Meters. And our denominator is seconds. So meters per seconds, right? Those are what our measurements would be. Okay. On part B, you have 2 to 4. So you're looking at g of 2, which again is 4. G of 4, which is 1. So you're calculating your A-rock. A-rock again, changing your Y. So 1 minus 4 over the changing your X, 4 minus 2. And we end up with negative 3 over 2. So this time we have a negative rate of change, right? So you have negative 1.5 meters per second. Yes? How do you feel? Application? All right, so you should have, those are your notes. We have our first performance task of the year. Yay, College Board.